and welcome. In our lesson today, we are going to discuss another factor that affects the rate of a reaction, which in this case is concentration. Now, generally, if you have a reaction whereby one of the reactants is a solution, an increase in the concentration of that solution will cause an increase in the rate of the reaction. A decrease in the concentration will cause a decrease in the rate of the reaction. Now, the reason for this is that when you increase the concentration of the reactant, you are actually increasing the number of particles present within that solution. So, which in this case, this also increases the chances of effective collisions happening. This speeds up the rate of a reaction. Now, if you were to reduce the concentration of that solution, you are also decreasing the number of particles present, therefore reducing the chances of effective collisions happening as such. Now, maybe just to remind ourselves what effective collisions are. For reactants to react with one another, they first need to collide with one another. Now, when they collide with one another, both reacting particles need to have the necessary amount of energy to form products. This energy is referred to as activation energy. Now, if they have the activation energy, they proceed to form the product. Now, this is when it's termed as an effective collision. That means that it has led to the formation of a product. Now, if the two particles don't possess the necessary activation energy, then they simply bounce away from one another and no product is formed. Now, let's imagine we have a scenario whereby we have two reactants as represented by the blue and green particles. Now, in the first instance, the number of particles present are few. So that means that the rate of the reaction will also be slow. But if we are to increase the number of particles or the concentration of one of the reactants as witnessed by the increase in the number of the blue particles, we are going to end up speeding the rate of the reaction. Why? We are increasing the chances of the particles coming into contact with one another, colliding into one another, leading to the formation of the product. So an increase in concentration increases the rate of a reaction. Now, let us do an actual example of a reaction that shows this clearly, that concentration affects the rate of a reaction. Now, in this reaction, we are going to focus on the reaction between magnesium and hydrochloric acid. Now, magnesium reacts with hydrochloric acid to form a salt plus hydrogen gas. The salt, of course, is magnesium chloride. Now, we have two petri dishes. Now, in these two petri dishes, we are going to have hydrochloric acid inside. The volume of the hydrochloric acid used is the same, but the difference is in the concentration. In the first petri dish, we are going to have hydrochloric acid that has a concentration of 2 molar. In the second one, 0.5 molar. So a higher concentration of hydrochloric acid, a lower concentration of hydrochloric acid. So what you're going to do is that we are going to take a strip of magnesium metal, place it in both petri dishes. Same mass of magnesium metal. Now, we are going to observe whether the reaction in the first petri dish, which contains a higher concentration of hydrochloric acid, is going to be faster. So let us observe. And there we have it. Now, you can clearly see that in the first petri dish, what is happening is that we are having a faster rate of effervescence. We are having more hydrogen gas produced within a faster time, as evidenced by the bubbles being formed. In the second one, hydrogen gas will still be formed, but at a very slow rate. So just by observing, we can clearly tell that the high concentration of hydrochloric acid is affecting the rate of the reaction. Now, up to that point, let me just summarize. An increase in the concentration of the reactant increases the number of particles present. This increases the chances of effective collisions happening, which in turn speeds up the rate of the reaction. Now, we are done with the first part of our lesson. So let us proceed to the second part, where we will be discussing past KCSE questions featuring concentration. Our first question is from 2019 paper 1. Describe how an increase in concentration increases the rate of a reaction. So concentration increases the rate of a reaction by increasing the number of reacting particles that are present. This, of course, increases the chances of effective collisions taking place, hence increasing the rate of a reaction. Okay, let's do another question. This is from 2007, paper 1. The diagram below shows a student's setup for the preparation and collection of hydrogen gas. Okay, so we can see that we are having zinc powder reacting with hydrochloric acid to produce hydrogen gas and zinc chloride. Part A, how will the final volume of hydrogen gas produced be affected if 80 cubic centimeters of 0.7 molar hydrochloric acid was used? Now, according to the setup, 100 cubic centimeters of 0.6 molar hydrochloric acid was used. So the volume was 100 cubic centimeters and the concentration 0.6. Now, if we were to change this to a volume of 80 cubic centimeters but a molarity of 0.75, then how will this affect the final volume of hydrogen gas? So essentially the question is asking, if we were to use this volume and this concentration, will it actually produce more hydrogen gas or less? Now, if you look at the information provided, you can clearly see that we are talking about a different volume, a different concentration. So you might assume that the volume of hydrogen gas collected will also be different. But this question is tricky. Now, if you were to calculate the number of moles of hydrochloric acid present in the first setup, you will find that it's 0.06 moles. How do we do this? Moles are given by molarity multiplied by volume over 1000. So the molarity was 0.6, the volume was 100, divided by 1000 gives you 0.06 moles. If you were to calculate the number of moles in the second setup, it will give you 80 multiplied by 0.75 divided by 1000, 0.06 moles. So the same number of moles. That means that at the end, the volume of hydrogen gas produced will be no different. There will be no change because the number of moles of hydrochloric acid in both cases is the same. Now let's look at part B. Give a reason why helium is increasingly being preferred to hydrogen in weather balloons. So there are two main reasons for this. Number one is that helium is less dense than air, so that qualifies it. And number two is that unlike hydrogen, it does not burn. And that, ladies and gentlemen, brings us to the end of this lesson. I hope it's been as enjoyable for you as it has been for me. See you next time.